Please read this disclaimer in its entirety. Today we're going to discuss geometric sequences and series. We should be familiar with arithmetic sequences, which have a common difference that is added to find the next term. Geometric sequences follow a similar idea, except that each term is multiplied by a constant to get the next term. This constant is called the common ratio. As before, geometric sequences can be described recursively. Here we define a starting value, then subsequent terms are described by multiplying the previous term by the common ratio. Repeated multiplication can also be expressed through exponentiation, which is how the explicit rule is written. Note that the multiplication of the first term is accounted for by dividing the initial value by the common ratio. The generalized formula follow the same pattern, both for the recursive rule and the explicit one, where the variable a represents the initial value and r the common ratio. Note that it's possible to incorporate the compensating division by the common ratio into the exponent. Unlike arithmetic series, which could be explored visually, geometric series are more easily attacked algebraically. We'll start by setting this finite series to be equal to a variable s. If we multiply s by r, it can be seen that most of this terms still match up, except for the first term of the original sequence and the final term of the multiplied one. Multiplying everything by -1 allows us to combine the two equations, which cancels out everything except the two aforementioned terms. Common variables can be factored out. The most important here is the s on the left side, because that allows us to isolate s, yielding an alternate formula for the geometric sequence. S can be replaced with the series expressed in summation notation. There are peculiarities with this. The series starts at 0, which means that n terms only go up to n-1, but the final formula actually uses n. We'll take a look at adjusting that in a bit. Let's see how to apply this to a real finite series. Because it's written in terms of powers, it can be easily expressed in summation form. The initial value would be 5, the common ratio r is 2, there are 10 terms from 0 to 9. These values can then be substituted into the formula from the previous page and simplified. This may be a good time to pause the video and think about what we've learned so far. The next section could be a little bit mind-bending, so it's probably worth being rested for that. The initial presentation on sequences and series in this video series suggested that infinite series can have finite sums. Let's explore this, first here with powers of 1/2. As you can see, the whole square fills up so that the final sum is equal to 1. Something similar can be done with thirds and thirds of thirds, which results in a series of powers of 1/3. Here we see that only half of the original shape is filled, so the sum must be equal to 1/2. This also works with fractions that are greater than 1/2, such as here where we start with 3/4 and add 3/4 of that space onto each previous square, and then repeat that process over and over again. Eventually, all 3 squares will be filled, leaving us with a final sum equal to 3. Being able to do this depends on each term in the sequence being smaller than the previous one. This happens when the magnitude of the common ratio is less than 1. If we look at the series definition from before and pay attention to what happens when n grows without bounds, we'll see that the r to the n term eventually goes to 0. The infinity symbol is used to indicate that the series continues without ever ending. There is no last term, but it doesn't matter because it vanishes. Here's an infinite geometric series that can be described with the derived formula. We'll use a starting value of 1 and a common ratio of 1/2. Substituting in the known values and simplifying will give us our answer. 2 is not what we'd expect from the squares animation earlier. That's just starting with this 1 out front. That, in turn, comes from starting at the index 0, which is already something we weren't really happy about. Let's see if we can do something about that. Here's the sequence, and we want to get rid of that leading 1. We want to end up with the series skipping that first value, so the index would start at 1 instead of 0, but if we add the starting value outside of that, it makes it equal to the series that we already have a formula for. Now we can subtract a from both sides to give us a new formula. A bit of arithmetic manipulation simplifies it to this new form, which looks exactly like the old form multiplied by r. If we take the original series with the 1, multiply it by r, you can see that we end up with the desired series with no leading r. Let's apply this to a problem. Start by writing down the formula, confirm that it matches our series, determine values for a and for r, and substitute them into the formula. Simplify this and find your answer. There's some room for confusion here with the two different possible ways of writing the series. You may encounter either one of them in the wild, so it's worth spending some time figuring out the differences and similarities to be able to use them appropriately when you encounter them. Use this opportunity to go back, rewatch pieces of this video until they make sense.